And I need to go back to my page 30 now. You probably do too. Back to page 30 because there's one more elaboration. No, it's page 29. The very last one. Solving problems involving fractions as an operator. Here's two problems for you. There's 7 students, or 1/4 of the class, who ride bikes each day, and 1/2 of the class who ride the bus. This is a year 4 type question. This is what they're going to have to be able to do. Now, how many? There's 2 ways you can solve this. Obviously, you can say, well, 7 students or 1/4. If 7 is 1/4 of the class, what's 4 times 7? There's 28 students in the class, right? Therefore, 1/2 of the class ride the bus, so that must be 14. Or maybe the students know that 1/2 is double 1/4, so you just double 7. Right? But the reason I'm showing you that is because the fractions are explicit in the problem. You can see 1/4 and 1/2, as opposed to this problem, which involves fractions but is implicitly shown. In a class of 24 students, you can see there's fractions. We're dealing and operating with fractions here. So they're the kinds of problems which you're going to be expecting in year 4 and will be, if not already, being tested through NAPLAN. Year 5, we get into more equivalent fractions, but also related denominators. This is not operating at all. This is simply saying what's larger, what's greater. 3/8 or 1/4. Again, the linear model, or hybrid between linear and area. Where's 3/8 on this mat? So just be prepared, you're going to see a lot more of these sorts of things. Right, so where's 3/8? 3/8 is here. Where's 1/4? Luckily they are related denominators. One denominator is a multiple of the other, or factor of the other, you might say. So I can utilise one of those to say, oh well, 1/4 is the same as 2/8, so 3/8 is larger. These are sorts of activities you'll be doing in year 5. And adding with them. So that was just comparison, now we're adding. So where's 5/8 on here? There's 5/8. So what we're going to do now is use a linear model, a number line, to do 2 things. We're going to find an equivalent fraction, and then we're going to use it to help us operate. 5/8, where's 3/4? There's 3/4 of 1. I need to start with 5/8 and add 3/4. So what is 3/4? 3/4, this is finding the equivalent fraction component. 3/4 is the same as 6/8. So now if I start with 5/8 and add 6/8, basically do this, I'm going to run along here and da-da-da-da-da, and the answer is 11/8. Right? So the linear model is good for doing that, isn't it? So I think we just got to get our head around these other models and be aware of these in order to achieve the elaborations that are in here. In year 6, we're going to be dealing with unrelated denominators. So here's some that are unrelated. One is not a multiple of the other, or a factor of the other. So what are we going to do with it? Find equivalent fractions first here. We're not operating, we're just comparing. So here's a fraction made again. 3/4, 2/3. They're not related, so we have to look for another denominator. Well, here's one here. 3/4 is the same as 9/12. 2/3. Oh, that's the same as 8/12. So what's larger? 9/12. Okay. Obviously, we work with multiples as a prerequisite, and there's a lot more number theory in here. I'm not even talking about this today. There's a lot more number theory. You'll get a lot more work on factors and multiples and prime numbers, etc. This essentially covers this, and I focus a lot on common fractions. Really, the only point I want to make here for the next 2 is this. When you go looking for subtraction, it's described under what they call additive situations. And that's because subtraction is the inverse of addition, right? Therefore, you can quickly surmise what they do for division. It's described under multiplicative situations. That's how you're going to find it. The last one is 2-dimensional shapes. In Queensland, but this is also true for most syllabus documents, you know, we describe these plane shapes on a heading called space. It is called a geometry in the Australian curriculum. And what you'll find is a lot more, well no, I shouldn't say a lot more, you will find classification of shapes. We don't do that in Queensland syllabus at all at the moment. In fact, if you look at, well, no, I don't actually say that either, but certainly not to the level as here. You turn to page 34 and look at the right-hand column. I know this is year 5, but look at some of the words which start these elaborations off. Under geometry, and classifying triangles and quadrilaterals. It goes further down, classifying triangles. Again, after that, classifying quadrilaterals. How do we classify these shapes? Well, in Queensland, we have never classified them inclusively. We've always classified them exclusive of the other shapes. So what does that mean? Well, I could get you to, we don't have time to do this, I did this yesterday with the teachers, but if we drew some three-sided shapes here, exactly 3 angles, what sort of shapes could you create? Well, here's some different ones, and we can describe them. This is what pretty much all we did in Queensland. We described this as a what? What sort of shape? It's a triangle. It is a isosceles triangle because 2 equal angles down here, 2 sides equal length. But you can classify them according to other things. In fact, this top line here, you describe them according to their angles. We'll classify them according to angles against the length of their sides. Right, well, what's an equilateral triangle? Equilateral triangle all have the same length sides. Isosceles is 2. What's an obtuse triangle? An obtuse triangle is a triangle in which its greatest angle is obtuse. A right triangle is a triangle in which its greatest angle is a right angle. Is it possible to have a right angled equilateral triangle? Can I put a check mark there? No, you can't do that, can you? So these are all, I guess, possibilities. Can I actually do it? Not possible, that's the wrong word. So these are all the cases. How many of those are actually possible? So you can classify them that way. You can classify them as another way of showing the classification of all the triangles. Here's the 3, according to the length of their sides. And for all those, I can have an acute triangle. That is, where the greatest angle is less than 90 degrees. But when it comes to right triangles, I can only have a scalene and isosceles right triangle. And obviously, for the obtuse angle, you can only have 2 of them as well. Can you picture in your mind the sequence of activities you would have to do in order to bring out that classification? You know, and most definitely, the language, exactly. Oh, yeah, that's right, sequence of development. I guess I've already made that point. And really, a sequence of development is most important to bring it out. What about quadrilaterals? That are the 3-sided shapes. What about the 4-sided shapes? What do you know about quadrilaterals? Here's the inclusive definition. What's a rectangle? You tell me, what is a rectangle?
Opposite sides of the same length.
Opposite sides of the same length. What else? Essentially, a rectangle is a shape which has two pairs of parallel sides, and all angles are equal. That's all you'd have to say. I had part of that wrong. You should say a rectangle is a quadrilateral that has 2 pairs of parallel sides and all angles are equal. That tells you there's four sides, right? So what's a square then? Because we all know it's a special rectangle. But if it's an inclusive definition, I have to describe it in terms of the rectangle. The square is a rectangle that has all 4 sides equal length. That's all I have to say. Because I'm including what the rectangle is. Right? What's an oblong? An oblong is simply a rectangle, it's not a square. How would you describe what a parallelogram is? What's a parallelogram? A parallelogram is simply a shape that has 2 pairs of parallel sides. No, parallelogram is simply a quadrilateral that has two pairs of parallel sides, right? And a rectangle is a parallelogram that has exactly two pairs of parallel sides, or that, and I've already said that, so simply a parallelogram that has all four angles equal. So we haven't done this before. And whenever we used to show a parallelogram, what did we draw? That. But that's a parallelogram. That's a parallelogram. That's what they've got to understand. I think kids, we did a good job of showing them the square is a special rectangle. But did we say a rectangle is, essentially this way? And what goes here? What goes above here? Between parallelogram and the top description. In fact, let's look at these, because this is everything we've done so far. What is something that all these quadrilaterals have in common? Well, they're quadrilaterals, so they have to have in common. What is something that quadrilaterals have in common?
Parallel sides.
Yeah, and be more specific.
Two pairs.
Exactly. All these quadrilaterals have exactly two pairs of parallel sides. Correct? That's pretty much all you could say in terms of them being quadrilaterals. But what other quadrilaterals could we draw that don't have exactly two pairs of parallel sides? Shapes like this? Right? So therefore that's the layer that goes above the parallelogram. So if I went back to this, that's what goes above there, it's a trapezium. So a trapezium is a quadrilateral that has at least one pair of parallel sides, correct? But there are some shapes that don't even fit that category. Some quadrilaterals that don't fit that. See a kite out here, where, the parallelogram, it's not one says a special trapezium, but a parallelogram has exactly two pairs of parallel sides. So it's like a trapezium, and it does have at least one pair of parallel sides, but it has exactly two. All this requires careful planning and developing our sequence. You can imagine the work that goes into developing that sequence. I think Peter said this day. He did say this when I was thinking of it. He said this: there can be no more scattergun approach. Peter Sutherland is the man who oversaw the riders, essentially. That's what my understanding of it. He oversaw the riders. And he said there can be no more scattergun approach. You understand what he says? It's not my quote, this is what he's saying. So no more, I'm going to do this today, I'm going to do that. He really, in order to teach a deep understanding of mathematics, it has to be a carefully planned sequence. And this prompted someone in the crowd to say, well, what about the investigative approach? And the response that was given was, I'll let you to figure out that. What's going to happen? So it was implying what might happen. Because that could be very much, we're going to investigate this, going to investigate that, but it's always in the absence of a sequence. And they wouldn't get political, they would not get political to answer that question. So, at the end here, if you want to download this presentation, this is not in your notes, you'll have to write this down, is if you go to this website, and if you want, you can just go to origoeducation.com and click on Professional Learning. Or you can type the whole thing in, which will take you to this page. And you see the arrow out here? It'll tell you, or not tell you, it's pointing to what you just downloaded, and that is a PDF.